morning, students. Welcome back to science class. Today we will start new chapter, that is human eye and colorful. The human eye and the colorful world. So we'll see that the working of the human eye is already later. So first we will discuss the colorful world. So before that we will discuss the defects of vision and their correction. Okay. So what are the defects of vision and their correction? Some people, okay, some people can read, some people can see nearer objects very clearly, and some people they can't see near objects clearly, and some people they can see the far objects clearly, and some people they can't see far objects clearly. Okay, I think you have seen some people they will face this kind of defects. Okay, so these defects we can call it as myopia, hypermetropia, and presbyopia. Okay, so first myopia or nearsightedness. Okay, myopia, nearsightedness, and second one hypermetropia or far-sightedness, and third one presbyopia. Okay, so first we'll discuss what is myopia. Okay, so myopia means is also known as nearsighted. A person with myopia can see nearby objects clearly but can't see far objects clearly. Okay, so myopia means what? So the person who can see nearer objects clearly but he can't see clearly the far objects. Okay, so this defect is called myopia or nearsightedness. See, for example, just imagine this is our eye. Okay, in our eye there is one lens is there. Okay, so that lens is convex lens. Okay, so that lens is made up of not glass, that lens is made up of jelly like material. Okay, so white colored jelly. Here, see, this is the retina. Okay, so light enters our eyes. Okay, so due to refraction light bends. Okay, if all the rays are converges at retina, so this is retina. Okay, if all the rays are converges retina, then we can say that eye is clear. There are no any defects. Okay, for myopia or nearsightedness, what will happen? These rays converges in front of the retina. Okay, in front of the retina. So that's why they see those who are suffering from these defects, they can see nearby objects clearly, they can't see far objects clearly. Okay, they can't see far objects clearly. So this defect is called myopia or myopia. Okay, so now how to correct this one? Some people they wear specs. Okay, they wear all the specs are not equal, all the specs are not same. Okay, some people they will wear different lenses. Those thickness of those lenses is bigger and smaller. Okay, so we'll see that later. Okay, now how to correct this one? So now our work is to make what? These rays should converge at retina only. You have to make that. Okay, so now here the rays are converges in front of the retina. Clear? So now how to make? Now here these two rays converges at retina. Okay, so to correct this defect, see here this myopia effect, it arises due to two reasons. Okay, that first one is excessive curvature of the eyelids. That is one reason, and second reason is elongation of the eyeball. Okay, it's very long. Okay, elongation of the eyeball. So clear. So due to these problems that myopia arises. Okay, so now using concave lens using concave lens. Whatever using concave lens, using concave lens. For example, see here. Using concave lens, we can correct this defect. Okay. So here I will keep concave lens. You know, right, what happens when you pass rays of light to concave lens? All the rays are diverges. All the rays are diverges. You have seen in the light chapter. Okay. So after reflection, the rays are diverges. Diverges like this. Okay. So then once again, both will converge. So clear? So we can correct this myopia defect using concave lens. Okay, so here we should use concave lens. Okay, what happens here? The rays are diverges here. Okay, so once again these rays strikes this convex lens. Okay, convex our eye lens. Okay, so once again here the rays are converges at retina. So clear? So this effect. So using concave lens, we can correct this defect. Okay, so this is the correction. So clear? Next move to hypermetropia. Okay. Hyper. So hypermetropia means what? Here, those are suffering from this defect, they can see clearly far objects. They can't see. They can't see clear objects. They can't see what objects clearly. Those are very near to them. Okay, so they can see far objects clearly. They can't see near objects clearly. Okay, so now in this case, in this defect, in this defect, here, those who are suffering from this defect, so here the rays are converges behind the retina. The rays are converges behind the retina. Okay. So here, so that's why they can't see near objects clearly, but they can see far objects clearly. Okay. So now using convex lens, we can correct this defect. Okay. See here. So if you place concave lens here, you know, right, when you, what happens when you pass rays of light to concave lens, all the rays are converges. Okay. So here also happened. So once again here also there is a convergence. Okay, so this is the correction. So using convex lens, we can correct this hypermetropia defect. Okay, so these two diagrams are very, very important. The correction of myopia and hypermetropia. Okay, so here see this defect. Okay, this defect arises. Here also there are two reasons. Okay, one is the focal length of the eye lens is too long. The focal length of this our eye lens. So this is also like lens, right? So which means it has a focal length. Okay, this focal length. Okay, thus that focal length is too long. Then second one, the eyeball has become too small. The eyeball, okay, it has become too small. So that's why this defect arises. Okay, so these are the two due to these reasons that my hypermetropia arises. Okay. Next, move to presbyopia. You know, for people those are older age, okay, what happens? They loses the sensitiveness of the eye. Okay. See, the power of accommodation of the eye usually decreases with the aging. Okay. You know, for example, when you cross 60 or above 65, 70, okay, they loses the power of accommodation of our eye. Okay. Means the near point gradually recedes away. They find it difficult to see nearby objects comfortably and distinctly without a corrective eyeglasses. Okay, so they can't see nearer objects and far objects clearly. Okay, so this effect we call it as presbyopia. So this happens when the age of the people increases. Okay, then this defect arises. Okay. See here, so this defect is called presbyopia. So it arises due to the gradual weakening of the ciliary muscles and diminishing the flexibility of the eye lenses. Okay, so you study later what are ciliary muscles. Okay, so this presbyopia arises due to what gradual weakening of the ciliary muscles. Okay, so when the age increases, okay, that ciliary muscles they become weak. Okay, so that's why this presbyopia defect arises. Okay, see this presbyopia happens when the age of the people increases. Okay, so this may arises after 55 or 60 or above 70. Okay, so to correct this defect, we have to use bifocal lens. Okay, bifocal lens. So here we have to use two lenses. Okay, so we can say that here presbyopia means it is both the myopia and hypermetropia. Okay. See, sometimes a person may suffer from both myopia and hypermetropia. So such people often require bifocal lenses. A common type of bifocal lenses consists of both concave and convex lenses. The upper portion consists of a concave lens. It facilitates a distant vision. The lower part is a convex lens. So upper part is a concave lens and lower part is a convex lens. Okay, means some people, okay, they will suffer from both defects, hypermetropia and myopia. So to correct, we use bifocal lens. Okay. Yes. So this is about the defects of vision and the correction. So next, move to refraction of light. Okay, so we have seen the refraction of light in lenses. So next, move to refraction of light in glass prism. So glass prism means, you know, it is in a triangle shape. Okay, so we call this as a glass prism. Okay, it is just like this. Okay. Okay, so tomorrow I will show you that prism. see here, glass prism means it is in a triangle shape. So now here, if you pass light, what will happen? If you pass light, what will happen? See, when you pass light to glasses, what will happen? It bends. So with that bending of light is called refraction of light. So now we will see here how it takes place. Okay, how the rays are bent here. See here, first rays enter from rarer to denser. Rarer to denser. So here we should draw that normal perpendicular to the surface. Okay. So now here a ray of light is traveling from rarer to denser, rarer to denser. So here the light ray bends towards the normal. So the light ray bends towards the normal, towards the normal. So now once again this ray will come outside, right? The ray will come outside. So here it emerges from, see here the ray of light traveling from denser to rarer, denser to rarer. So here also at the point of incidence will draw normal. So now here that ray which bends away from the normal, away from the normal. So now we call this is a emergent ray. Okay, emergent ray. So incident ray, refracted ray, and emergent ray. So clear? You know already this angle of the angle between normal and the incident ray is called angle of incidence, and this angle is called angle of refraction, and this one the angle between normal and emergent ray, so we call it as angle of emergence, angle of emergence. Okay, suppose see here this is the actual direction of the light. Okay, so this is the actual direction of the light. Clear? See here, but here light ray bends here. Why? Because here we have kept prism. If you won't keep that prism, what will happen? So then light ray will move in a straight line. Okay. Now just observe here. If you extend this line, it is the emergent ray. Okay. So its extends means it will move directly. Okay. So we call this one. Okay, this angle. Okay, so we call it as angle of deviation. Okay, so this is the actual path of the light, and then when you extend this emergent ray, okay, see actually you know the rays, this is the bent, right? Why? Because here this light it strikes this surface, so that's why it bends. Okay, but just think in another angle. If you extend the direction, then it will come from this direction, right? This emergent ray. Okay, so the angle between this original path and this, okay, we call it as angle of deviation. Okay, so this is the refraction of light in glass prism. The refraction of light through a glass prism. Glass prism means what? It is also made up of glass only. Okay, so this is the refraction of light. So next move to dispersion of white light by a glass prism. Suppose, see, if you pass a different color, yellow color light, red light, red color light, and whatever, so you will get this kind of what refraction. But if you pass white light to glass prism, and then we will see what will happen. Okay. So you know the sun from sorry, the light from sun. So that is example for white light. So if you pass white light to glass prism, what will happen means which splits that white light, which splits into several colors. Okay, when you pass a white light to glass prism, what will happen? Which splits into several colors. Which splits into several colors like this. Okay, see here. Okay, with that white light which splits into several colors, and we will get this kind of pattern. Okay, this is V I, G, B, and G, yellow and orange. So we will get this kind of pattern, that is V, I, D, G, Y, O, R. Vibgaya. Okay, Vibgaya. Okay, see here, which indicates what that white color which is made up of several colors. This white color is made up of several colors. But when you pass this white light to glass prism, what will happen? That white light which splits into several colors. Okay, and always we will get these colors. Okay, in this format only. Okay, see, if you use another prism, you won't get first violet, then red, then indigo. Not like that. Always you will get this kind of pattern only. That pattern is Vibgaya. Okay, so here violet, indigo, blue, green, yellow, orange, red. Always you will get the colors in this pattern only, in this order only. So here we obtained here some band of colors, right? So this band of colors we call it as a spectrum. Okay, so we call it as a spectrum. Okay, and this entire process, when you pass white light to glass prism, that white light which is splits into several colors. So we call it as a dispersion of light. Okay, so what is a dispersion of light? Dispersion of light, the splitting of white light into its component colors is called dispersion of light. Okay, the splitting of white light into its component colors. The splitting of white light into its component colors is called dispersion of light. Okay, so suppose if you pass a red light here, then you won't get, because red light is not made up of several colors. Only a white light is made up of several colors. So example for white light is the light from sun. It is a pure white. Okay, so when you pass a white light through glass prism, so we will get these kind of colors. Okay, so this process is called what, dispersion of light. Dispersion of light means what? The splitting of white light into its component colors. Okay, yes, see here, now here I will keep, and one more here. Okay, see here, why we get these colors? So why? Because see, the different colors they bend with the different angles. The different colors they bend with the different angles, which depends on the incident ray. Okay, so here this red light which bends least, and the violet which bends more. Okay, the red color which bends least, and the violet which bends more. Okay, next, suppose I will keep one more prism. I will keep one more prism in inverted position. In inverted position. In inverted position. In inverted position. Okay. So once again, refraction, here also refraction takes place, right? So once again, they will reflect like this. Okay, so from finally we will get once again white light. So clear? When you keep one more prism here, what will happen? So once again we will get white light. Okay, these all several colors, what strikes this when they passes through this prism, then once again we will get white color. So here you have to keep in this position only. Suppose if you keep like this, then you won't get. Okay, so this here. This observation gave Newton. This observation gave Newton the idea that sunlight or that white light is made up of several colors. Okay, so this idea, okay, give the Newton idea that what the white light or that sunlight is also white light. So that white light or sunlight is made up of several colors. Okay. Next, so see, this is happens when you pass a white light through glass prism. Okay, I think see here actually we won't get 7 colors. Here actually we won't get 7 colors. Rain drop. Okay, so here first what happens means here first it refracts. First it refracts. Okay, then here once again it undergoes here total internal reflection. Total internal reflection. Okay, see here total internal reflection means suppose see now this is rarer medium and this is denser medium. Okay, you know you have seen you have studied in the 8th standard. Okay, so after critical angle, so here these rays bends like this. Okay, if you take one more ray, bend like this. But after 90 degree, the rays they will reflect back to the same medium. They will reflect back to the same medium. So we call this is total internal reflection. Okay, see here when the rays travel from denser to rarer, see this total internal takes place when the rays travel from denser to rarer only. If you pass from rarer to denser, then you won't get that total internal reflection. Okay, so here some rays they undergoes what refraction, but after critical angle, critical angle means 90 degree. 90 degree, the rays, okay, all the rays are reflect back to the same medium. So we call it as total internal reflection. Here also some rays they comes outside, but after 90 degree, all the rays once again they will reflect back to the same medium. Reflects back to the same medium. So here what will happen means here this color which splits into several colors. So here also in the rainbow also we can see maximum 3 to 4 colors. We can see maximum 3 to 4 colors. We can't see all the 7 colors. So here also that is due to the overlapping of the colors. Okay. So this is how the rainbow is formed. So next move to atmospheric refraction. See, you might have observed the apparent random wavering or flickering of objects seen through a turbulent stream of hot air rising above the fire or a radiator. You know, see, just imagine this is a okay. So just imagine this is a fire. Okay, this is a fire. Clear? So above the fire, for example, here fire is there. Okay, so above that fire, if you observe some objects, here fire is there. You are here. You are observing above the fire. You can see some kind of air. Okay, if you observe the objects, means at the behind the fire. Okay, so fire is there. You have to observe the objects. Means above the air. You have to observe those objects. You have to observe those. You have to see those objects through the through the air. That you have to that air it should be above the fire. If you observe the objects just above the fire, then you can see those objects they will fluctuate. Okay, you can see those objects just they will do like they will do just like a dance. Okay, you can see some kind of fluctuations. Okay, that is due to the refraction of light. You know, for example, see just above the air, that air it is very hot. It is very hot. Okay, that is very hot. You know that light from the objects they should come from cool air to hot air. Cool air to hot air, then once again to cool air. Okay, so here also the refractive index of hot air and cool air both are changes. Hot and cool air. Hot and cool air. So this hot air which is a little bit less denser compared to cool air. Okay, this hot air is little bit less denser compared to cool air. If you take hot air and cool air, so here out of these two, this hot air is a rarer medium, then this cool air is denser medium. So that's why if you observe the objects just above the fire, those objects will fluctuate. Okay, those objects just look like a once those are just look like a they're dancing. Okay, so this is we call atmospheric refraction. Clear? Next, move to twinkling of stars. Twinkling of stars. Okay, see here, those stars are there. The distance between us and star, there is a huge distance. Okay, if you want to travel, you can't travel. You can't reach those stars. Okay, see, to travel from Earth to Moon, it takes lot of time, correct? But if you want to travel from Earth to stars, it is a huge distance. Okay, even that light, it takes what thousands or millions of years. Okay, see, the speed of light is, right, that is 3 into 10 raised to the power 8 meter per second. This is the speed of light. For this light, it will take years, thousands of years to travel to reach those stars. Then what about us? Okay, so it is very different. See, we can't travel. Okay, maybe in future we can travel for stars. Right now, what we have technology. So using that technology, we can't travel to stars. Okay, yes. Now just observe here. That stars. Okay, just imagine this is one star. Okay, see, this is Earth. Okay, just imagine somebody standing here. Okay, so our Earth is made up of different layers. Okay, if you go above, then you can see there are different kinds of layers. Okay, so the atmospheric, which is not uniform. Okay, which is not uniform, the arrangement of particles in the layers, that is different. Okay, so when you come down from sky to the land, so at that time the refractive index of the surfaces which keep on increases. Okay, suppose if you take from sky to the surface of the earth, at that time when you come, okay, when you come down, at that time the refractive index of the surface which increases. Okay, the refractive index increases. So now see here, the rays from these, see the light from the stars. Okay, the light from the stars, what will happen? So when they enter into the earth's surface, at that time the rays, they will bend. Okay, or just to see this example, the pool of the depth of the swimming pool, it appears to be raised, right? We have seen in the late chapter. See here, when you keep one coin here, okay, when you keep one coin here, what will happen? Okay, so this is a coin. Clear? So now this coin, if you observe from this side, what will happen? This coin, which is actually which is appears to be raised, which means if you extend these lines, they will, both the rays are meet at this point. Okay, so then the position of this coin, it appears to be here. Okay, so why? Because here you put water here. Okay, see, this is the actual position of the coin, and this is the apparent position of the coin. Okay, but when you remove the water, then you can't see this coin. Okay, so when you put water, then you can see that coin, but you are not, see, you can't see the actual position of the coin, but you can see the apparent position of the coin, which means here the rays, what will happen here? See, the rays they should travel from denser to rarer. At that time the light rays, they will bend. Okay, these rays, okay, for our eyes, these rays just looks like what? These rays are coming from this point. Okay, the same process or the same process takes place here also. Okay, so the rays, what will happen? Here the rays are bent. Here the rays are bent, and for our eyes, looks like these rays are coming from this point. Okay, so that's why the star's positions looks like here. Okay, so we call this is apparent positions of apparent position. Okay, so actual position is here only. Why? Because these rays while enter to the earth's surface, what will happen? The rays bends. Okay, you know here also the rays bend rays. So these bent rays are, for our eyes looks like these bent rays are coming from this position. It's not right. Actually, the rays are coming from this position. So that's why for our eyes it looks like the position of the eyes here. Clear? The same process here also. Okay. Suppose if you are observing what at the night you are observing one star. Okay. That actually is what you are observing in the night time. It's not the actual position of the stars. It is the apparent positions of the stars. Okay. Next move to why these stars twinkle. Okay. See here, if you consider these stars, okay, some amount of light enters. Okay. See, light ray means that is the light is made up of million rays. Okay. See, these are for our the size is very small. Just size of the stars just looks like a dot. Okay, which means what? The light from one dot, which is very less, right? But they can that light which more distance. Okay, if we consider this is a point source, then they will enter to our eye. For example, see here. Okay, just imagine these rays are coming from stars. Okay, so when these rays are enters to the Earth's atmosphere, what will happen? Some rays they will refract this side and this side and this side. For your eyes can see or these only few rays strikes your eyes. Okay, so what will happen with for our eyes, which looks like just like a fluctuating. Okay, so that's why the stars are twinkles. Okay, then why don't the planets twinkle? Okay, see the distance between Earth and stars, that is huge. The distance between Earth and planets, it is very less. For us, the size of these planets are bigger than these stars. Actually, see that is for our eyes, you know, but the size of the stars is very huge. Okay, see our star, 13 lakhs of Earth, 13 lakhs of Earth is equal to one sun, and these stars are 100,000 times greater than our sun. Okay, but they are huge distance. The distance with these stars and Earth is very huge. So that's why those stars looks like a very small in size. But these planets are closer to us. Okay, so that's why these objects what looks like a bigger in size. Okay, see the planets are much closer to the Earth and are thus seen as extended sources. If we consider a planet as a collection of a large number of point-sized sources of light, if you consider this planet as a large number of point-sized source of light, the total variation in the amount of light entering our eye from all the individual point-sized sources will average out to 0, therefore nullifying the twinkling effect. See here, the light from this planet, okay, so the light from the stars, this is very less. Why? Because the distance is more, but the light from the planets, okay, we can receive more light, means the huge rays. So what happens? So the that refraction, that bending of light, it nullifies that average, which is equal to 0. So that's why the planets they won't twinkle. Okay, why? Because here the huge number of rays are comes. Okay, so here here only from stars our eye. Okay, only few rays strikes our eye, but the light from the planets. Our eye strikes more rays compared to here. Okay, so here our eye, which our eye can see a large number of rays. So that's why the planet it won't twinkle. Okay, so this is a twinkling of stars. So I will stop here. Tomorrow I will continue the class. In the tomorrow's class, we'll discuss advanced sunrise and delayed sunset, scattering of light, tyndall effect, etc. Okay, thank you.